which answer did you have a 4 in?
55.
Number 55? Okay, you're going to have to dictate it to me because I neglected to bring my book today. Hold on a minute. Number 55, Zechariah says. This will be good. Take a peek. All right, what was the problem?
2 when t is greater than or equal to 0 and less than 3.
What?
F of t equals.
Oh! Okay. 2 when t is what?
Greater than or equal to 0 and less than 3.
Okay.
And then it's negative 2 when t is greater than or equal to 3.
Okay, excellent. Okay, good. So first things, and we're supposed to come up with the Laplace transform. Probably. And you want to know where the 4 came from?
Yep.
Okay, let's do it. So first off, we need to have this thing. Now we could, of course, you could choose to do this using an integral. Well, who wants to use an integral when we can use the unit step function? So this is going to be 2 times, oh, it's just 2, right? It's 2, and then you're going to subtract off 4 times the unit step function at t minus 3. There. And so is it this 4 right here that you need to know where it came from?
Yeah, that's what I was wondering about, because in the example we did yesterday, there was no minus 4.
Okay, well let's graph this thing. Well, here, we'll graph it first, and then we'll see where the 4 came from. So here's the graph of this function. So here's 3, and then suddenly we end up down here. There we go. Okay, so first of all,
4 is the difference.
yeah, 4 is the difference.
I just, apparently, in the example we did yesterday, apparently I wrote it down wrong, so they didn't line up with what I was doing in the answer, so that's why I was confused.
Okay, but now it makes sense?
Sure.
Okay, so the 4, anyone else need a 4? We got the 4. And then the Laplace transform of this is easy. We can do this. Loss of f of t is going to be, what, 2 over s minus 4e to the negative 3s over s, something like that. Look, that back of the book right? Hey, I love it. All right, what else do we need to take a look at? You can do these differential equations? Yeah, did you have to do any that were actually differential equations? You didn't have to do a differential equation? Who picked those? That's ridiculous. Okay, here, this is going to be number 73. I'm just going to, is there a 73? I hope not.
Yes.
Okay. This is number 173. There's probably one in there. There should be one that is an actual differential equation, but this will answer your question because it'll be both directions. To do a differential equation with a unit step function, you got to go both ways. So let's just pretend that we're going to solve this differential equation using, let's see, so this is going to be u of t minus 2. Hold on a minute. I need to make this smaller. I got a little too excited when I put that 173 on there. Okay, and then we're going to subtract off, okay, u of t minus 3. Okay, so the stuff on the left is oh, and I need an initial condition. So y of 0 is equal to 0, just to make it simple on ourselves. So the stuff on the left, you understand what that is. That's a differential equation. Although I noticed on the quiz, or I think it's either the quiz or the exam, or whenever the last time I looked at something you did, that some of you are still having trouble understanding how to write this. So this is good that you asked the question to do the whole thing, because there's still a little bit of confusion about how to deal with that left-hand side there. But the right-hand side is the new stuff. Now here's what's happening here. Now this wouldn't be a spring mass system. We can make it into one. Here, let's do that. Here, make it a double derivative and change this to a plus 4, just to make it a little bit easier. Yeah, I know I'm changing, but that's all right. Because remember, this is problem 173. So, okay, there we go. So I got my spring here anyway. So what's happening here is that it's just sitting there doing nothing, as you can see. And then at 2 seconds after we start the stopwatch, all of a sudden a force is applied, and that force happens to be, how big? Oh, just 1, the force of 1, whatever. Anyway, this force is applied, and so it's applied, and then it goes away at 3 seconds. So that's what's going on. So we should expect something like that to happen, that all of a sudden this thing starts moving. So let's see if we can, if this actually bears itself out in reality. So we'll solve this thing. First of all, the Laplace transform of the second derivative, and then you've got 4 times the Laplace transform of y is equal to, I'm just going to write these in here because I happen to know them, negative 2s over s minus e to the negative 3s over s. So yeah, you could think of this forcing function as just being you're applying a force just for a small interval of time, and then it goes away, but you're left with the aftermath. You're left with, there's consequences to applying that force. Yeah, I mean, don't want to get too political, but yeah, even after something happens, like you turn on some tariffs and then turn them back off, there's still some ramifications, and it would take some additional force to right things and steady the ship, so to speak. But yeah, like I said, don't want to get too political on the situation. But it's true, right? That when, yeah, so, okay. But anyway, getting back to this, let's go ahead and apply this. Let me go back up here to, where is it? Where did it go? There it is. So here's my stuff here. And I guess what I just want to point out that the second derivative, same thing with the first derivative, is you have this s multiplied by the Laplace transform of your y. I know most of you are doing this, but there are a couple of you that I noticed didn't do this correctly. So you have the s1, you have just a single s for y prime, y double prime gets a double s, 2 s's, triple prime would get 3 s's, and so on. And then you start subtracting off initial conditions, but I cleverly made the initial conditions nothing, so we're sort of a steady state, everything's at equilibrium, and then we apply this forcing function for a period of time, and then we watch as things bounce up and down and the markets go haywire. Oh, once again, I'm sorry, I shouldn't get Chick-fil-A, just remember Chick-fil-A. Okay, so here we are. So let's go ahead and see if we can apply this to this thing. So you have s squared times capital Y of s. So the capital Y, that's another thing, is that the Laplace transform of y is capital Y of s. So so we're just using capital Y as a stand-in for the, so I don't have to write Laplace transform over and over again. I don't know, that might be causing problems. So you have that minus s times the initial condition, this one, minus the initial velocity, which I made them both 0 just because I don't want things to be too ugly. Then I'm going to add to this 4 times the Laplace transform of y, and that equals this stuff, which I don't want to have to write again, so I'm just going to copy it. There it is. There, isn't that nice? So like I said, it seems like, I can't remember what the situation was, but there was a quiz or something where some people were leaving out the s times the Laplace transform of y when you're doing the second derivative or first derivative. Okay, now that we've got this, we want to solve for the Laplace transform of y. So here we go again. Here, just a sec. Duplicate. There, I just don't want to have to write if I don't have to. So let's see, this is s squared plus, does that look right? Yeah. Nice. All right, now, you know what I'm going to do is, in order to make my life easier, yeah, I can guarantee that the quiz is not like this, in the sense that, well, it won't be quite as complicated because it's only a first derivative, not a second derivative. But anyway, here's what I'm going to do, s times s squared plus 4. Okay, so I've solved for this y of s. What I did here is I just factored out all of these e to the negative s's just to get them all alone, because that's not going to, this is the big problem child here, is this, dealing with that, that fraction there. Does that look all right? Okay, let's do our partial fractions. I know, I made it up. I better do it. Okay, what am I doing here? I don't know. Okay, so let us deal with this. Where am I going with this? Here we go. I'll do it up here. 1 over s times s squared plus 4 is a over s plus bs plus c over s squared plus 4. Since this thing is a quadratic, you need to have a linear factor on top. Some of you are like, yeah. Some of you are just now realizing that you've been doing it wrong all of your life. Okay, so then we get 1 is equal to a times s squared plus 4 plus bs plus c times s. Okay, for this one, I'm going to actually use the book method to figure out my a, b, and c. But you could use you could still do the plug-in, plug in 0. Actually, why don't we do that? Let's plug in 0 to figure out what a is, just because that's going to be the easy one. So let's do s equals 0, gives me this. Oh, that's a 4. Come on. Yeah, 4a. Because s equals 0 makes that 0, and it makes that s squared 0, so that looked good. So that means that a is 1/4. And then that gives us this. 1 is equal to 1/4 times s squared plus 1 plus bs squared plus cs. I'm running out of room. As you can see, I'm impinging upon the purple stuff, so I better get this done. So hopefully you can see what's going to happen from here, but just in case, notice that there's a 1 on the left, a 1 on the right. So we can cancel those. And then hopefully you can see this, that there's no s's over there at all. So c times s, since there's nothing to cancel with that, c has to equal 0. And then b has to equal -1/4, so that b and this can cancel, because that's 0 over there. So that's kind of a hybrid. I used my method plus the book method, but do what it takes to get the coefficients so that this is easy. Now that I've got all that, let me zoom back out and put this into right here. Yeah, I know you can hardly see it up there, but I'll make it in red so you know where I'm using this stuff. So I have 1/4 is a, so 1/4 times 1 over s. And then b is -1/4, so I'm going to write it like this: -1/4 times s over s squared plus 4. Probably would be nice if I just got rid of the 1/4 altogether, factored that out. So that's the next move, I suppose. Okay, let me just pause, because I'm almost to the point that is going to make Mariah happy. Where she wanted to do some inverse Laplace transforms. So, I've been doing the forward Laplace and doing some fun partial fractions here. But I want to make sure that everyone's happy with the partial fractions and getting the e to the -s and all that stuff. Does that look good? Okay, if you're happy with that, then now we get to do the inverse Laplace transform. But first, I need to spread everything out, because it's all condensed here. So let's spread it out so that we can have lots of room to do this. So here's what I mean by that. I've got y of s is equal to 1/4 times all of this stuff. So I'll just put a square bracket at the end as well. So what's all the stuff that I'm going to multiply by 1/4? It's going to be e to the -2s over s minus e to the -2s over s. I know, so far, so much fun. Minus e to the -2, oh, that's a 3. Sorry, that should be a 3. I know someone was looking at that saying, what's wrong with this guy? Yes, that's right, something. I don't know what. S squared plus 4. I keep thinking about that kayak. And then this is e to the negative 3s times s over s squared plus 4. And then we can close off that. So I kind of just wanted to, that way I can deal with these things one at a time, be a lot easier. All right, we're okay. Wait, I hope Cooper's watching. Wow. Yeah, we should put a little Easter egg for him in here somewhere. I'm not sure what. Well, something of, wait, do you know what musical he's in? Okay, too bad. Maybe it's Oliver. A little, like Charles Dickens, Oliver. Oh well. Okay, so it probably isn't, because that's, it's probably something like The Wiz. No, that's even too old nowadays. Okay, so now we'll get to y of t. Let's finish this up. This is the best part now. So this is what we've all been waiting for, is the inverse Laplace transform. So we'll do these one at a time here. That one's easy, right? That's not a problem. That one you can just look up. That's going to be the Heaviside, or sorry, I keep saying that. It's the unit step function, t minus 2. So that one's easy. Okay. The next one is pretty easy as well. It's also a unit step function, t minus 3. Now things get tricky. So here's how I would do this. I'm going to recognize that because of the e to the, here I'll highlight this, because of this, I'm going to have a unit step function. So let's just write that down. Let's get it out of the way so that we know that we have a unit step function. So unit step function, t minus 2. That's what that green highlight sort of indicates. But I need to multiply this by something. The something I'm going to multiply it by is whatever the function that has a Laplace transform of s over s squared plus 4. But we know what that is. You've got it. You've got it on your quiz that you had last time, and it's on this quiz. You probably have it memorized. It's the cosine, isn't it? It's cosine. Cosine of t? No, cosine of 2t, right? Because of the 4 there, cosine of 2t. So, but here's the tricky thing, is that the Laplace transform, maybe I'll do this in pink here real quick. So the Laplace transform of cosine of 2t is indeed s over s squared plus 4, but because of that shift, the shift is going to make this into the cosine of 2 times the quantity t minus 2. So it gets shifted the same amount as this. So those shift the same amount. We're nearly done. One more. The last one is pretty easy. We already know what it's going to be. It's going to be the Heaviside function, or sorry, yeah, it's hard for me to shift, isn't it? So the unit step function, t minus 3. And then now this is the same cosine, isn't it? This s over s squared plus 4. It's the same thing that we had over there. But you're going to shift it by 3 units. And that is it. Oh, the 2. That is it. Okay. Now, the next thing I gotta show you this, because this is now, I should have gotten it prepared on Python, but I don't know the Python to do the unit step function yet. So sorry about that. So I'm gonna have to go back to my old school here, and use. Let me just make sure. Let's see. Plot the side of t equals 0, negative 2 to 2. Okay, yeah, that's it. All right, I just wanted to make sure I knew my syntax. Give me a sec. I want to plot this because it's amazing to me. So we have the, so it's just take me a minute to type all this in. I'm going to ignore the 1/4 because the 1/4 doesn't really play into this. Okay, here's what I find amazing about this. This function is continuous. It's a continuous function. It makes, now here, think about what I mean by this, is that function is going to describe the position of this mass as it goes up and down. So even if the forcing function is discontinuous, as it is, if I were to move my hand up, hit this thing, push it upward, and then move my hand away, which I'll do right now. Okay, so there was a discontinuous force applied to that, but that mass didn't like move like instantaneously from one position to another. This is continuous, even though it has all of these discontinuous elements to it. So I wanted to just graph this. I know we're blowing a lot of time here, but it's so much fun. So this might save you from some homework if we do it slowly enough, right? At least that's what Zechariah is thinking. So yeah, I'm just kidding. Okay, just a sec. So heavy side, t minus 3. Give me a sec here. Minus t minus 2 times the cosine of t minus 2. And, 2 times t minus 2. I forgot my 2 again. Almost done. Plus, okay, let's see if this does it. Oh yeah, that's amazing. It's incredible. Okay, so here's the actual graph. So here's what happens is you're going along, minding your own business, and then at 2 is when the force gets applied. I typed in, here, I'll show you. I typed in that solution exactly the way that we just found it. I don't know if you can see it up here. It's up there. Except for the syntax, because this is old school. This is like from 1997, literally, this program. Um, it uses heavy side instead of unit step. But heavy side of, so this is going along, and then you have this discontinuity, but it's not, because it kind of cancels with the cosine here, and you get this curve, and then the force stops being applied, but because this thing continues to bob up and down, here it goes, up and down. I just find that incredible, but maybe it's not as impressive to you. But, okay, that's enough of that. Yeah, so here's my, let's go back to the answer there. Anything else about this? So did that answer your question about the inverse Laplace? Or yeah, so the main thing is you just, when you see this, you think, okay, I'm going to put a unit step function in there, take everything else, figure out what it is, and then apply the same shift, and you'll be okay. All right, excellent. Okay, I misprinted. Is this okay? Sorry, everyone's laughing at me for some reason. Yeah, I was worried about like my fly sound. Okay, so I misprinted. I misprinted my quiz. Well, I only misprinted half of them. So some of you are going to get a defective quiz, and some of you are going to get a non-defective quiz. If your quiz has this delta on it, then it's the wrong one. I just didn't fix that part of the. So anyway, it should be this, and it's only a single first order differential equation. So you take what you get, and if yours is printed correctly, you get lucky. And if it's not, fix it, and then you'll be lucky as well. Or no, you won't be lucky, you'll be blessed, because here you are. There's a bunch. Here's one. Here. There's an extra. Make sure you put one in that spot, like a missing man formation type thing for Cooper. All right, did everyone get one? Almost. Oh, nice. Okay. So yeah, so if yours says delta, change it to the unit step function. If it's the unit step function, then you're doing great. So some of them, mine is the delta, so I'll just suffer with this. Oh, there it is. Freeze this thing. Bless you. Okay. Test. Test. Go, puffball. All right, hopefully you're almost done, and you can finish up. It's surprisingly similar to the one that apparently I really like, those sorts of numbers. But, oh, now you're worried? Yeah, no cosines, don't worry, no cosines. If you have a cosine, you're wrong. Oh, you don't have a cosine? But you still don't want to give it to me, apparently. Oh, Taven's like, yeah, you got it. It's, oh, oh yeah, oh yeah. Uh, where is it? Oh, here it is. Here, it all got wrinkled. It was in the bottom of my bag. So it has a hole in it, but it still works. Yeah, I better put that in the grade book, though. I don't think I put it in my grade book. All right, you have another minute while I get this in the grade book, apparently. It's what's that, test 3? Test 3. All right, excellent. I got it in there. You can bring it home and show your mom. Okay, hopefully you're done now. Oh, did I take yours, Haven? Where did I put it? Oh, I found it. Found it. Very good. Let me see if you're right. Hey, it looks pretty good. Nice job. Excellent. Good job. I'm liking it. All right, you're still working. Good job. You got something. Nice. Lovely. No, you don't want me to?
Almost there.
It wasn't that bad of a partial fraction. Come on.
No, it wasn't.
What's wrong with the partial fractions?
It's not. It's the everything else.
Oh, okay. You do your other thing then. There we go. Very nice. Good job. Very nice. Yeah. Okay. That's good. Cooper, you're feeling good? Wait, you did the wrong thing? Oh, I see what you did. Okay, I'll just grade yours the way you did it. You didn't correct. You did a second derivative. Yeah. No, I see what you did. You just changed the U. He's still writing. Yeah, it's my fault for not fixing my typo. Yeah, that one look good. This one look good. All right, very nice. He's still writing. Max, feeling good. Anyone else? 8, 8. Okay. Right. Oh yeah. Well, we'll see. Do you have it memorized? So that you can compare when I hope you have it memorized. All right. Yeah. It doesn't have to be simplified. You could just box up what you have.
Yeah.
Oh, you haven't done your inverse Laplace transform yet.
Yeah, I did.
Oh, you
that's
did.
What I'm doing right now.
Oh, that's what you're doing now. All right. Oh yeah, then you're almost done. Yeah, just
Yeah.
put the exponent in there. Yeah, take your time, but please hurry up. Oh wait, there's someone else working here. Oh, you're just putting that final inverse. You don't? It looks like you know. All right. Yeah, let's have it. Let's have it. Good job. All right, let's do this. Oh, we're Andrew's. Sorry, got it one here. Okay. Here, we've got more rubber bands. Okay, so let's see what I did. Hopefully I got it right. Let's find out. So here it is right there. So here's the crucial starting point. I kind of skipped a step here, but you have S times the Laplace transform of Y minus the initial condition, but the initial condition was 0, plus 4 times the Laplace transform of Y. And I just factored out the S plus 4. And then I've got this stuff. I kind of cheated. I didn't really cheat. I just factored out the 1 over S. So it's this over S and this over S. In fact, because I remembered from when we did the homework problem, number 173, that it was easier if you factored. Then, let's see, we have this. And you look at that and you say, well, drat, I'm going to have to do some partial fractions, which you will. Not that bad, though. The partial fractions, look at that. They were so quick. It was the same 1/4 from the earlier thing. So 1/4 times this minus 1. I know I didn't even show my work, but this is simple enough. You could probably do in your head yourself. So that's what we got. And then I did the same thing I did on the 173. And oh, wait a minute. I skipped another step. It's hilarious. So I should have done the, FOIL. There's the 1/4. And then you can see that you've got e to the negative 2s over s, e to the negative 4s over s, and then this is the s plus 4 thing, and the s plus 4. So, is that okay? Good enough? Okay, we're moving on. Okay, so what are we doing now? I don't know. I'm trying to find my thing. No, this is quick. This is a quickie. There's like 4 problems for homework for Monday. They're quick. So here's what we're doing is we're hitting golf balls or hitting springs. So so the Dirac delta function, what it is, I didn't bring my hammer, but it's probably good that I didn't because I'd probably injure something. So I just have this roll of stuff here. So if we hit something like the ball there or this, there it goes. Well, that was weak. Let's try again. Oh, that was a little bit too, see, that's what I was worried about with the hammer. I'll do one more try. If I'm a little bit in between those two, that'll illustrate the delta function. So, but the delta function is an impulse. It is a sudden impulse like that. Oh, that was a good one. So you have this, everything is going along just fine, and then all of a sudden, boom, something gets hit. So impacts like this, when you're impacting a ball with a club or a bat, that's an example of the delta function. Now, of course, this isn't happening instantaneously. It's not instantaneous like in a mathematical sense. What's really happening is both with the hammer or this thing and with the club. When the club impacts the ball deforms a little bit, doesn't it? You probably don't know this, or you probably, you're familiar with this idea that the ball is going to deform a little bit. You'll have a slightly inelastic, what is it called? They kind of crunch together a bit, and then the ball will separate. But it happens in such a short amount of time that we can model it with an instantaneous impulse. Just like with this, when I hit that with this, of course, what's happening with this, it's not the metal that's deforming, it's this roll of paper towel. And so when I push it up there, it deforms a little bit and then it goes up. But that very short amount of time that the two things are in contact can be modeled by an instantaneous impact. And so here's how this is going to look. This delta function is we're gonna model it like this, but this isn't what you're really going to care. So don't draw this because this is just the beginnings. Is we're going to imagine that the impact is going to occur at time t0. And so we'll take a little bit of time on either side of t0 and say, okay, the impact is spread out along that amount of time. So perhaps it's a half second on either side, or maybe it's a millisecond on either side that you spread out this particular impact. The important thing about this thing is that the impact itself, this delta function, has an area of 1. So the area here is 1 inside this, just to standardize things. Now, of course, if I hit this harder, then I'll just multiply this delta function by some constant. So this might be a delta function of 1. And then if I want to go to 2, I would double the amount of, it would be 2 times the delta function, would be just twice as much force. So whatever the units are, but this is the way we're going to model this. Now, here's the thing, though, is like I said, we're going to try to imagine that happens in an instant, in a split second. So it doesn't get spread out like this. This is reality. But the way we're going to model this is we're going to take that and we're going to smush it together so that the impact is modeled by a very, very tall, very, very skinny, discontinuous like impact right there, this very tall spire, if you will, so that it's just in an instant you have this one impact. So that is the delta function, and that's the thing that was on the defective quizzes, the delta function at time t equals 0. So very similar to the unit step function. It's discontinuous. It's actually quite simple to come up with the Laplace transform for this, because all of these things, this thing is a limit. It's a limit of a bunch of unit step functions. So this is the limit as a goes to 0 of this thing right here. So if you want to think of this as being, basically this is just 2 unit step functions that are combined. So, you go up and then you go down. And so if you do the limit as a goes to 0, then you get the delta function. So the delta function itself is just the limit of some unit step functions. And because of that, you could relatively easily figure out the Laplace transform of this thing. We're just going to write the Laplace transform. Now this is kind of, I don't know, the way that that is written is not the greatest, but it's one way to visualize this or to imagine it, is that the delta function is 0 until you have this one impact, and that impact goes up to infinity. I know, it's ridiculous, but, and then you go back to 0. But this thing, this integral, just is this idea that the area that we're dealing with, the amount of force, is just 1 for this thing. So this is a forcing function. It would be 1 unit of force, whatever the units are for the problem you're dealing with. Okay, now that we got that sort of squared away, let's deal with the Laplace transform. It turns out that the Laplace transform of this is almost exactly like the Laplace transform of a unit step function. So it's really fascinating. The Laplace transform of a unit impactor, this Dirac delta function, is just this. It's just looks very similar to the unit step function, but without the s on the bottom in the denominator. So this is going to behave similarly to the unit step functions when you have a forcing function that's discontinuous. If I impact this, I mean, we can visually see it, that if I hit this, if I actually had a hammer, which would be much more, if I had a hammer, right? Maybe we could, oh, I looked up the musical. It's not a musical, sadly. It's a play, so that you can all go and see this. Just a minute. Thought you might be interested. Here it is. So it doesn't look, I was kind of disappointed. It looks like, I don't know what this is, switching principles. So, yeah. But yeah, we can go. I was hoping it was something that we could make fun of, but I don't want to make fun of the principles. So we'll just leave them alone. But anyway, getting back to this. So just like with the unit step function, if I hit this thing, you can see that the mass there doesn't instantly, it's not like Star Trek where you have the teleporter. It doesn't teleport from one place to another. It's continuous location. It's just that what is discontinuous is the forcing function. So let's do a problem like this, and then we'll be all done for the day. So here, oh look, that looks sort of similar to what you had on your quiz if you had the defective quiz. So what is this? This is, you know what, yeah, I want to start off, why not? We'll leave it the way it is. It may cause a little bit of grief if we leave it that way, but I'll leave it. So what this is you have this, it's actually very similar to this, because the y double prime, it could be a spring mass system, or it could be an RLC circuit, but whatever it is, it's something that could be, has some sort of a cyclic nature to it. And then we have our initial conditions. So let's go ahead and set this up. I'm just going to do the left side pretty quickly. I will take my time on the right side. So on the left side, you know what? I'm going to do this on Notability. I can't stand doing this in PowerPoint. Give me a sec. So you shut this back. Is that thunder? I'm going to say, it's like, I'm so tired of having to bike in the rain. Okay. Come on. There we go. Okay, there it is. Okay, so there it is again. So let me do the left side relatively quickly. I'll talk through it though, just to make sure that you see what I'm doing. I'm going to, again, as always, y of s, capital Y of s, is the Laplace transform of little y of t, just so that we have that squared away. So anyway, this second derivative is going to be s squared times the Laplace transform of y minus s times the initial condition, or initial position rather, minus the initial velocity. So there's the that piece. And then plus, so that was all of this. And then we have the Laplace transform of y. And then we have to deal with this Dirac delta function. The 4 is just going to go along for the ride. This stuff, since this is a unit impulse, we're just going to do e to the negative and then wherever it is. So it happens to be 2 pi units after we start this thing going. So I guess that this was kind in the sense that, so this thing starts off, its position initially is 1 unit away from equilibrium, and then we wait 1 cycle. That's what that 2 pi means, is we're going to wait 1 cycle, and then we'll hit this thing with a hammer. So it'll go down, up, and then boom, we'll hit it when it's down or up or whichever direction it is. So that's what that means there. It's 2 pi is just when it's going to get hit by whatever hammer you've got. Now, what's that? No. Oh, yes, it does need an S, sorry. I was thinking of the one in the denominator, like the unit step function, but no, it does need an S, thank you. Anything else, other things I've got wrong? All right, now, yeah? What's that? Oh, it sure will, yep. Yeah, anytime you have anything like that, like a second derivative, second order differential equation, usually you're going to get a sine curve, sine or cosine. So, all right, let's wrap this thing up. This isn't too bad. So we have s squared plus 1. And then over on the right, you've got 4e to the negative 2 pi s plus s. Now this is happy. There's no partial fractions that we're going to have to deal with. Isn't that great? No partial fractions. We're going to divide this out, and we're going to be happy. So check it out. When we divide things out, you get this, 4e to the negative 2 pi s over s squared plus 1, and then s over s squared plus 1. Incredible. So I think we could all do this at this point, probably. But just in case, because this is what we had for homework for today. So the only new thing, so this is why this is an easy day, is because the only new thing is understanding this in the context of starting off the problem. But once you get the problem started, you will never end with that. Your solution will never have that in it, because the solution will always have some sort of a unit step function, and we're going to see what that is in just a sec. So see if you can come up with the correct unit step function. I guess you might not have a little table, but you can find your table somewhere. Maybe I'll go grab a table and pull it down here. Freeze this. Just a minute, I'll go grab the one from above. Good enough. Copy and delete. What in the world? What's going on up there? Okay, I've got my table so that you can see it if you need it. There it is. I know it's really little now, sorry. I'll try to make it a little bigger. Okay, so the hard one is the first one. The second one is super easy, so because it's staring you right in the face, I hope. But the first one's the hard one. So let's put that one together. We'll work our way through this. Oh, I haven't even done. Yeah, I never did attendance. I guess I can just pull this up to remind myself, since it's apparently a federal law that we have to do this. He doesn't. Yeah, he doesn't know. Well, we were told multiple times this year. Really? Maybe he goes back to his office and clicks it. You don't think so?
I guarantee he just puts everyone in.
Well, he could do that. I mean, that would be doing attendance. But yeah. Okay, we'll randomize this. Whoops, let's try again. Randomize. There we are. Madison, you know that what's going on here, don't you? What kind of a step function are we dealing with whenever you see this? Perfect. T minus 2 pi. So we're doing the unit step function t minus 2 pi. So that's the first thing you should think of when you see this is, let's deal with that first. We got it. Now, nice. Now that's going to be multiplied by something, so let's figure out what it's multiplied by. And to figure that out, I'm just going to highlight for you this stuff. And I realize that this is going to get shifted, but ignore the e to the negative 2 pi s just for a sec and see if you can figure out what you're going to be multiplying this by. So when you see 4 over s squared plus 1, what does that make you think of? So Max, do you have a function that corresponds to this yellow stuff here? This, yeah, very good. The sign. And did you want to put the argument in there? You can if you want to.
It would be sine of 1t, 4 sine of 1t.
Okay, yeah, okay. So 4 sine of 1t, very good. I assumed that that's what you meant, but just to be sure. So you have the 4. The 4 is just going to be 4 times sine of 1t, because notice right there, the omega, or w, if you want to call it w, is 1. So very good. So this is 4 times sine of 1t, but when we write it down here, instead of doing 4 times sine, so 4 times sine of 1t, we're going to change the t to match this stuff right here. So here, I'll even put a 1 here just for fun. So t minus 2 pi. So you get whatever it is that you need, and then you're like, oh, wait a minute, I'm going to change it so it matches the unit step function. Okay, now we'll do the easy one. The easy one, hopefully everyone's got. Tyler, do you know what this s over s squared plus 1 is? Yeah, it's just cosine of t. It's right up there. Second one down. Very nice. So that's the cosine of t. And look at that. Done. So when you do the homework for today, you're going to see these delta functions. Just bear in mind, they shouldn't show up in your solution. The solution will never have a delta function in it. It'll always have just the unit step functions. This, by the way, is also continuous, even though it's got a discontinuous piece to it. It all matches up. Okay, so I'm going to stop the recording so Cooper can't hear us talking about him.